Hello everyone and welcome to a new chapter in mechanics, which is chapter 2, linear momentum. In this part of the chapter, we're going to cover the definition of momentum or linear momentum simply, and how to calculate linear momentum for an object or for a system of objects. Let's get started. Before we start, I would like to take a look at this picture in which a young man is practicing skateboarding. If you have ever tried this sport, you should have suffered from the idea of balancing on the skateboard. At least I did. Skateboarding is definitely a sport that's hard to master. Not only that, at the early stages, to balance and anticipate the motion of the skateboard itself is truly hard. Stand on the board and try to move forward a bit. If you move slightly forward, the skateboard rushes backwards. Now, why does that happen? And how can we control it in case we want to practice this sport? We'll try to answer the physics behind these simple terms of skateboarding. As a first step, let's start by defining what linear momentum is. Linear momentum is a vector quantity which is the product of mass and velocity of a particle or an object. P vector equals m dot v vector. So you notice that in linear momentum, we combine two terms, which are the mass of an object, and the mass is related to the amount of matter in that object, and the speed, or more specifically, the velocity of that object. So if I want to describe the motion of an object, I can go to momentum and use it as a full description, including the mass and the velocity. Don't forget that velocity is speed and direction, right? As for units, I think that all of you are familiar with the units adopted here. So just pay attention to conversions in case you are doing any calculation. The last sentence is linear momentum is close to the term quantity of motion. Now, it's important to specify the term quantity of motion isn't something scientific or a physical term, because simply motion cannot be quantized, guys. Motion isn't a quantity. Motion is a state. But if you want to describe that state as high amount of motion or high ability due to the motion, we can simply refer to the linear momentum. Take a look at these two pictures. A car and a truck are moving at the same speed. Now, the car has less mass than the truck. So if you ask yourselves, which of these two cars or these two vehicles have more ability to produce motion or to produce effects on objects, let's say if it crashes into a wall, which one can produce more effect on the wall? Simply, we can all think about the truck. And if I ask you why, you will say because it has more mass. Now, if we take the same example, but the car is moving at higher speed than the truck, we all know that the speed of the truck may or may not compensate for the mass of the truck. Okay, so the speed of the car might compensate for the mass of the truck or not. It all depends on values. If you want to get numerical and compare the quantities of motion or the abilities of these two objects, all you have to do is just multiply their mass and their velocity. On the other hand, if we have a system of many objects together, let's say a man and a skateboard together, for example, to calculate the linear momentum of that system, which is a vector, all we have to do is just add the vectors of momentums of these objects. We denote that by summation of pi or simply sum of mi vi. As an example, if you look at the figure here, a boy and a girl are pushing against each other. Both are on their roller skates. Okay? Now, as they push, in order to calculate the momentum of the system made up of the boy and the girl, all we have to do is just add P1 plus P2. P1 is mv1, P2 is mv2. These are vectors. To continue with vectors, we must add a certain axis. So you notice here we added the x prime x axis, which is horizontal and to the right hand side. And we denote by I as the unit vector along that axis. By this, if you look at the figure and the axis that we've chosen, you notice that the girl is moving in the positive direction, whereas the boy is moving in the negative direction. So P of the system is 48 times minus 2.5, because the 48 kilogram skater is moving in the negative sense, while the 40 kilogram skater is moving in the positive sense. That's why the 40 is multiplied by plus 3. After that, we simply calculate, and here accidentally the momentum is 0, meaning that both have opposite linear momentums. Now, would that mean anything for us? I will not give any comment until further explanation and studying in this lesson.
So, what we have seen so far is that linear momentum P equals mv, right? It's a vector quantity which can describe the state of an object. We also have seen that momentum of a system is simply the sum of momentum of all individual particles. Now, on the other hand, when you go to a system of particles, we all remember how to calculate or how to determine the center of mass. The position of the center of mass is given by summation of mi ri over m total. Now, if we rearrange this equation, moving the summation of mi to the left-hand side, we get r vector multiplied by the total mass is summation of mi ri. R is the position, right? If we derive with respect to time, we know that the derivative of position is the velocity. So we get the equation dr by dt is 1 over m, which is the same as summation of mi. This is the same as this part, multiplied by summation of mi dri by dt. Don't forget here that we are assuming mass to be constant, and that will be our situation in general. One more further step, we will have this equation. M total multiplied by the velocity of the center of mass equals summation of mi vi. Hence, as a conclusion, we can add one third equation. Linear momentum of the center of mass is equal to the summation of mi vi is equal to the linear momentum of the system. So these three equations define linear momentum mathematically, linear momentum of a system of objects, and at the same time linear momentum of the center of gravity or the center of mass of the object. Take for example daredevil or a cyclist attempting a jump on his motorcycle. As this cyclist jumps at a certain point, the motorcycle and the cyclist are detached. The motion of the cyclist and the motorcycle isn't random, isn't arbitrary. If you take a look, what you can see here is the trajectory followed by the center of mass of both the cyclist and the motorcycle. Instant by instant, if we draw the velocity vector of the system together first here, or the system which is composed of both the cyclist and the motorcycle separated, together they produce the same velocity vector, or to be more accurate, the same linear momentum vector. By this, we will be able to determine or foresee the motion of the cyclist or the motorcycle depending on the other's motion. Okay?
Now, let's go to solve an application which highlights the ideas that we have covered so far. So we are given two blocks that slide or are sliding on a frictionless plane such that m1 is 1.2 kilograms moving with v1 3.6 meters per second along I, and we have another mass m2 moving with a speed v2 being 2.4 along j. So we have two-dimensional exercise here in which we have two particles, each one is moving on one of the two axes. Calculate the linear momentum of each of these two blocks, deduce the linear momentum of the center of gravity, and in which direction is that center moving. Now, at this level of the course, and in grade 12 in particular, you don't need to know the difference between center of gravity and center of mass. We treat them as if they are the same thing. Starting with the solution, first in part 1, calculate the linear momentum. Okay, so we start by applying the equation P1 equals mv1 as a vector quantity, which is 1.2, and we kept the speed as a vector. So we have 4.32 or 32 kilogram meter per second along I. Now some people might prefer to write this as 4.32 I, and aside we write the unit kilogram meter per second, which is also accepted. So don't be keen about any of these, use whatever or whichever you find suitable. On the other hand, P2 is M2V2, but we just have to pay attention that P2 is along J. That's it. Now, in part 2, deduce the linear momentum of the center of gravity, and this is a direct application of the idea of P, linear momentum of center of mass, is the linear momentum of the system, which is nothing but P1 plus P2. So we add these together, but since we have two independent vectors, one along I and one along J, we have to stop here. Now, would anyone like to continue and find the magnitude and direction? Feel free to do it, but this is more than enough as a vector. You all know that vectors can be represented as x and y components, right? In part 3, in what direction is the center of mass moving? So the question here highlights the center of mass. So the two particles are moving. One is moving like this, and the other is moving like this. One is moving along x, the other is along y. So together, if we visualize them, the center seems to be moving sideways like this. Now what is this direction? How can we find it out? This is what we're going to treat in this part. To determine the direction of motion, we can use the velocity vector, right? And since velocity, by the way, is related to momentum, we can simply say V of center of mass equals P over mass total. So P of the center of mass equals P as vector over M1 plus M2, which is 4.32 over 1.2 plus 2 here, and along J this. So we get V being 1.35 and 1.5, one along I, the other is along J. In order to find the direction, we remember from grade 11 or from previous math classes that direction can be determined by the angle formed with the x-axis or the abscissa or the horizontal. So if you look at the figure to the right hand side, you notice that Vx and Vy are drawn. Angle beta here, which is the angle between the horizontal and the center of mass, can be calculated by using trigonometry. So by the geometry of the figure, tangent beta, which equals opposite over adjacent, is 1.5, which is Vy, over 1.35, which is a Vx, 10 over 9. Then using the calculator, beta is how much? 48 degrees. So we can simply add to this a simple point or a simple description. The center of mass moves along a line forming 48 degrees with the I direction. Summing things up, we have seen that P equals m times V as vectors. We have seen that P is in kilograms meter per second, which is direct, mass is in kilograms, and speed is in meters per second. We also have seen that P of a system is nothing but summation of Pi, just add the vectors of the other momentums, or we can simply say P of the center of mass. Now this or that, they are both alike. It all depends on the situation and the problem that you are solving. Okay? That's all concerning this session. Make sure that you know how to calculate this, how to deal with the vectors involved here by applying the concepts and the ideas we have covered in the upcoming exercise. Our first exercise for this chapter is extracted from the National Book for Grade 12 in the Lebanese system, which is number 12, page 43. In case you don't have the book, here is the text. We are given an inertial frame with three masses. The coordinates along x, y, and z, which are sometimes variable with respect to time, are also given. We are supposed to determine the linear momentum of each particle, then the whole together. Then we are supposed to find speeds or velocities. Here I just remind you that v equals dr by dt, right? So to find the velocity, we can derive the position vector. We can derive on x alone, on y alone, and on z alone. Try to solve this on your own, and I think by now you all know that at the end of each chapter, we post a video in which we solve all these exercises together. Okay? I hope that what we have covered today was grasped by everyone. If you have any problems, go over the video again and don't hesitate to write any question in the comments or just text me about it. Okay? Now, ending our session the same way we've started it when we studied skateboarding. In skateboarding, athletes try to control the momentum of the center of mass of themselves and the board itself, thus anticipating the motion of the skateboard upon any move. How's that? Simply, your body and the skateboard form one system. If your body moves, the whole momentum of the system will change. So the skateboard will move in a direction according to that change, either to prevent it or to get along with it. We'll talk about these in more details further in the chapter. Okay? Thank you for the time being. Go over the exercises that we have assigned, and we'll meet again in the upcoming session.